So last time, and I think you missed it, Manny, the last time we talked about how a lot of these arc length and surface area problems have a very kind of specific style of equation that you're going to be asked to find the arc length or surface area of. And they often look something like, let's grab this one here. Let's say we want to find the arc length of, what do we got here? Sure. X equal to y to the fourth over 4. Is that the same one I did last time? Might be. Fine. We'll do it anyway. Plus 1 over 8y squared from y equals 1 to y equals 2. What I want to point out about this kind of style of thing is this is the kind of thing where when we find your ds, a very specific type of thing happens. So we know the arc length, and I like to write it as capital L like your book does. Arc length is the integral of ds. Just adding up all the s's, right? You could try to graph this. I don't recommend it. It looks kind of weird. And depending on how your function's written, it's going to be one of 3 ds's, right? Your options for ds are, just to point out over here, your ds options are, you don't see this one a whole lot. This is the one we started off with, dx dt squared plus dy dt squared dt. We did one example like that parametrically. We'll see that again maybe at the end of the quarter when we talk about parametric and polar equations. And then we have 2 other versions. We have the one we used last time, which was 1 plus dy dx squared dx. Essentially, you just are rewriting this first one, saying that x is equal to t and that y is a function of x instead of a function.
Wait, so I wasn't hearing last time. What is this?
So, sorry, say that one time?
I'm just confused.
Sure. So the idea is we've got some curve here, right?
Yeah.
X is a function of y. I could maybe try to draw it, although it's not going to be great. If I plug in x equal to 1, I get 1/4 plus 1/8, which is 3/8. So when y is 1, x is like 3/8. Again, this is not going to be a perfect graph. It's just going to be, right. And then when y is 2, x is going to be 16 over 4 is 4, plus a little bit more. Sure, a little bit more. So, and I don't know what this looks like exactly. It might look something like this. Who knows? So the idea is we want to find the length of this curve. And so we're going to break it up into little pieces. So that little piece right there, we're going to call that tiny little piece ds, a small change in the overall length. But the problem is, unlike previous things we've done, where we've broken things up into little pieces, usually it's been a small change in x or a small change in y. But this small change in s, well, if we blow that up, it kind of looks like that, kind of exaggerating the curve there. So there's my small change in s. And the idea is we can think of that as, well, I've got some small change in x and some small change in y. And I can approximate this small change in s using the Pythagorean theorem. So that red line there, that length, is approximately ds. And that length is equal to, well, Pythagorean theorem, the square root of dx squared plus dy squared. Or if you do it just the mathematically tricky way and divide everything and multiply everything by dx, here's what you get. You can say it's equal to the square root of dx squared plus dy squared over dx times dx. But then if I want to bring that dx into the square root, I've got to square it. So this ends up being, I'm kind of running out of room here, the square root of dx squared over dx squared plus dy squared over dx squared times dx, or in other words, the square root of 1 plus dy dx quantity squared dx. That's kind of like the math tricky way to do it. So this type of, when you see something looking like this, where it's like something with a power, something else with a power, you should be aware that the following type of pattern almost always happens. when we try to find the integral from y equals 1 to y equals 2 of, oh, I forgot the third one. So if you've got if you've got y as a function of x, this is what you do, right? dy dx, y as a function of x. If you've got x as a function of y, your ds is going to be the square root of 1 plus dx dy squared dy. So basically, whatever thing your function is, whatever variable your function is of, that should correspond to your d whatever here. So since I see that x is a function of y, I know I'm going to be using the one with dy. I ran out of room, so I'm going to use another piece of paper. Okay, so but here's what I want to point out. This specific type of problem has a very kind of well-known pattern that always kind of happens. So what's going to happen is when we find the integral from y equals 1 to y equals 2 of the square root of 1 plus dx dy squared dy, here are the things to look for. Dx dy squared will have a middle term that is negative 1/2. And then what's going to happen is you're going to add 1 to it, and it's going to factor back the same kind of way it already factored, except the middle sign changing just a little bit. Let me show you what I mean. But I just want to say this happens a lot. So we've got x equal to, I'm going to rewrite it as 1/4 times y to the 4th plus 1/8 times y to the negative 2nd. And now let's find dx dy. So the derivative there is going to be y to the 3rd minus 1/4 y to the negative 3rd. A key indicator that the thing that I know is going to happen is that after I take the derivative, the powers of my variables are opposite signs. One of them is positive something, and the other one is this negative of the same something. So that when I square this out, and I do dx dy squared, which is y to the 3rd minus 1/4 y to the negative 3rd squared, I'm getting, well, I know how to square things like this. It's the first thing squared plus 2 times the first thing times the second thing plus the second thing squared. But look at that. The middle term is exactly going to be negative 1/2. I've got y to the 6th. I've got 2 times y cubed times negative 1/4 times y to the negative 3rd. The y cubed and the y to the negative 3rd multiply together to give you y to the 0th. Right? They cancel each other out. And then 2 times negative 1/4 is negative 1/2. And this last part over here is plus 1/16 y to the negative 6th. Why is this notable? Well, because now what I'm going to do is I'm going to add 1 to it. So I look at this, 1 plus dx dy squared. Here's where the magic happens. I'm going to do the same thing, except the minus 1/2 is now going to be plus 1/2. So I'm going to get y to the 6th plus 1/2 plus 1/16 y to the negative 6th. And because we've already done the work of taking y cubed minus 1/4 y to the negative 3rd and squaring it out, it's not too hard to see that this, of course, has to be y cubed plus 1/4 y to the negative 3rd quantity squared. That's the magic. That whenever you have something that kind of looks like this, you take the derivative, you see those powers look the same, and you square it out, and the middle term is negative 1/2, it factors back really nicely once you add the 1 to it. So here's the whole story. If I'm going to calculate this integral here, do I have enough room? Yeah, I have enough room. This is going to equal the integral from 1 to 2 of the square root of 1 plus this derivative, y cubed minus 1/4 y to the negative 3rd squared, dy. But we know that when we add 1 to it, we get that, which is that. So we're going to get the integral from 1 to 2 of the square root of y cubed plus 1/4 y to the negative 3rd quantity squared. And I was going to do something. So I just want to point out, right, this sign here corresponds to that sign there. And this sign here corresponds to that sign there. And then the rest of this is easy. The square root of something squared, they undo each other. So we get just the integral from 1 to 2 of y cubed plus 1/4 y to the negative third dy. And here's where things start to feel kind of really silly. It's like you've taken this big circular walk, and when you do the integral of this, you end up with almost exactly the function you started with. Oh, which I didn't write down. Which I'll write down up here. The function we started with was y to the 4th over 4 plus 1 over 8y squared. When we integrate this, we get y to the 4th over 4 minus y to the negative 2nd over 8. Almost exactly the same function we started with, except that the middle sign has changed. It's kind of cool. It kind of feels terrible that we did all this work and got back to essentially where we started, but there's no other way to do it, really. I mean, you could know what the answer is going to be, but someone still is going to probably expect to see this work on the exam. So even when you see something like this, you're like, oh, great, I know the answer. Once I find the Arclength, it's going to be like the same function, except opposite sign. And then we just plug in and we get 16 over 4 minus, I would probably think of this as the y squared in the bottom. So 1 over 8 times 2 squared minus, and then 1/4 minus 1/8. Whatever terrible number that is. Right, exactly. It's by design, because if they're not this pattern, there's very few other examples where the integral is doable. That's kind of why. So I will point out let me just show you one other kind of example. So I'll give you one more example but we're not going to do it. So I would just point out on your own, I would encourage you to maybe say, let's say our function is, y equals 3/4 x to the 4/3 minus 3/8 x to the 2/3 plus 5. Plus 5? Sure, why not? Where x goes from plus 5 seems weird. Does that seem like it's gonna? Yeah, it's gonna work out just fine. So here's what I'm going to say. I don't want to do all the work, but I want you to on your own at some point. So I'm going to tell you that if I find 1 plus my derivative squared, I take the square root of that, which is my ds, that's going to exactly end up being, oh, I got to do the integral too. Sure. It's going to be fine. It's going to be x to the 1/3 plus 2/3. Yep. 1/4 x to the negative 1/3. That's what you're going to get when you do all the work. You should check this yourself. And so then when you integrate this, you're going to get exactly back the function you started with, except without the plus 5 and with a different sign. Question?
I don't know.
Just these types of functions. It just happens to be a hallmark of these particular types of functions. And finding Arclength specifically. Definitely not. They're not enabled functions where it's easy to calculate the Arclength. One other example, which I think is kind of interesting, is let's say we want to find, and again, this was the Arclength. So for this one, you would end up getting, right, your answer, quote unquote, would be the integral from 1 to 8 of x to the 1/3 plus 1/4 x to the negative 1/3. That right there, that's your ds, which is that. Here's another interesting example. Let me shout to this one. I want to find the Arclength of y equal to the integral from negative 2 to x of the square root of 3t to the 4th minus 1 dt, where x goes from -2 to 1. Sorry, to -1. Apologies. Seems weird that I want to find the arc length of this curve. But it seems weird exactly because it's designed to be relatively easy to calculate. dy dx here is the derivative of this integral. Fundamental theorem of calculus says that's going to be the square root of 3x to the 4th minus 1. And then if we're going to do this arc length thing, it's relatively easy to calculate. We're trying to find the length being the integral from -2 to -1 of the square root of 1 plus dy dx squared. Well, look at that. Dy dx squared is just 3x to the 4th minus 1. So this is going to end up being the integral from -2 to -1 of the square root of 1 plus the square root of 3x to the 4th minus 1 squared. Right? It's by design made to be easy to calculate. The square root of this squared is just 3x to the 4th minus 1. The ones cancel. And we're going to get the integral from -2 to -1 of the square root of 3x to the 4th. And the square root of x to the 4th is just x squared. So it's going to be the integral from -2 to -1 of the square root of 3 times x squared. Okay, we integrate, we get the square root of 3 times x to the 3rd over 3. From -2 to -1, we plug in, we get the square root of 3 times -1 over 3 minus -8 over 3. So we get some weird number, 7 root 3 over 3. So if you see one that looks really bizarre like this, it's because they're trying to make it easy to calculate the derivative of this, so it turns out to be something nice when you square it and add 1 to it. That's why they're making up silly looking problems like this, so that it's easy to calculate the arc length. Questions about any of the things I've said here? I would say the biggest takeaway when you're thinking about arc length, and we'll see in a minute, surface area, is that you want to remember that for finding arc length, you're doing the integral of ds, where ds is one of the 3 things. Typically the square root of 1 plus the derivative squared. That's, in fact, that's a very general state. ds is equal to the square root of 1 plus your derivative squared. D whatever makes sense. Okay. Where'd you go? So for surface area, let's look at the following example. So let's find the surface area of the quote unquote bowl formed when we revolve the curve y equals x squared, where x is between 0 and 2, about the y-axis. Okay, so let's draw a picture. So I'm just taking y equals x squared, which looks like that, and revolving around the y-axis. I'm doing this kind of deal. And we're taking a rubber band, right? So when I think about my slices or my strips, right, I'm taking a little bit of the length here. There's a little bit of ds, and I'm figuring out how much area there is when I sweep that length around my bowl. Question? Uh-huh. Well, I mean, ds is this square root of whatever thing, right? But we do need to use ds. But L and DS are really kind of the same thing. Right? When I'm thinking of L, I'm thinking of it just I'm adding up all the DS's.
You don't have to go, you're not using Y. That's what I'm saying.
Correct. We're not using DY.
Reason just as that shit.
Not might be, definitely is because, right? It's not a straight vertical or straight horizontal. It's a curve that's traversing both horizontal and vertical distance as we go along it.
So a bunch of the steps will not approach each other.
Say that one more time.
A bunch of the steps will not approach each other.
Right.
Okay.
So here, this rubber band shape I'm sorry, terrible. So the area of my strip is going to be circumference times length. So it's going, so if we call this ds and this your radius, then the area is going to be, and how do I like to write this? Yeah. Surface area is going to be 2 pi times my radius, there's my circumference, times my length of that part there, or the height, if you prefer, like if the height's not quite the right word, but we'll go with it. Height, width, whatever you want to say of the word there. Length of the length of the height, sure, we can say that. That sounds terrible, but whatever. So in this particular case, now here's where things get a little bit funky. You can kind of do this any way you want, which sounds dumb when I say it, but what I mean is you're not really restricted to using specifically X or specifically Y around any axis. Things get weird though. So I'm going around the Y axis. This rubber band has a radius of, well, how far am I from the Y axis? I'm X away. Or, well, no, not or. So my radius here is X, because I'm imagining this little section I'm looking at is located at X away. Because X has to range from 0 to 2. But that rate, just like it's very, very similar in thought to the shell method, right? Where our strip was located X away from the axis of rotation when it was the Y axis, or Y away from the axis of rotation when it was the X axis. So here, our surface area of our band is going to be 2 pi times X times the square root of 1 plus my derivative squared. And if we want to actually find the total surface area, we add up all the areas of the rubber bands. So my total surface area is going to be the integral from x equals 0 to x equals 2 of 2 pi times x times the square root of 1 plus dy dx, which is 2x squared. Now I should point out, if someone had asked us to find the length of this, we couldn't have done it. Meaning that if you were just integrating the square root of 1 plus 2x squared, oh wait, you can totally do that one. No, you can't. Oh, well, we can just later on. Sorry. We don't have the tools yet to do just the length of x squared. Because it's more complicated or requires trig substitution. But this we can totally do because it lends itself really, really easily to a u substitution. So if we rewrite this, I'm going to pull out the 2 pi and roll from 0 to 2 of the square root of 1 plus 4x squared dx. We can totally let u equal 1 plus 4x squared, and our du is 8x dx. So 1 over 8 du is equal to x dx. And I lost my x here when I rewrote this. Apologies. There's my x. I need that. So then we can rewrite this as 2 pi times 1/8 du. And then here I've got the square root of u, or u to the 1/2. I like to change my limits of integration. So I'm going to go, instead of x equals 0, I'm going to say u equals 1 plus 0. Instead of x equal to 2, I'm going to u equal to 4 times 4 is 16 plus 1 is 17. Then we integrate. We've got pi over 4. The integral of u to the 1/2 is 2/3 u to the 3/2 from u equals 1 to u equals 17. And since we changed our limits of integration, we don't have to go back and plug in what u is equal to in terms of x. We just plug in 17 for u, and we get pi over 6 times 17 to the 3/2 power, which is gross, minus 1 to any power is 1. And that would be the very strange number that is the surface area of this ball. Question? Probably not. I mean, some people do. When I took this class, we definitely did the methods of integration first and the physics and like physical stuff later. So we could do that, but they've changed the way it's done for some reason. It's kind of weird. I don't really know why they've done it that way, but that's what people have decided to do for some reason. So yeah. So no, probably not. Yeah, of course. So I changed my limits of integration. I used my u substitution, which was u equal to 1 plus 4x squared. So if x is 0, u is 1. If x is 2, cool. Let's look at another example. So the weird thing about this is, yeah, let's go around the x-axis. So now y equals x squared. X is between 0 and 2. But now we're going around the x-axis. A similar shape, well, a similar curve we're starting with, but then we're going around this axis here. My pictures could be better. Okay, so my lower band, same kind of deal. Okay, so now the surface area of my band, once again, is 2 pi times my radius times my ds. And that's really what sticks in my head when I'm doing surface area. So arc length is just the integral of ds. Surface area is the integral of 2 pi r times ds. Basically, the circumference times the length. So now, if we're going around the x-axis, we're imagining that our radius is how far we are from the x-axis, which is what? Which is y. Right, so our radius here, is y. But I want to do things in terms of x, because I've already got things written in terms of x. So I'm going to say my radius is x squared, because that's what y is equal to. So sometimes, well, it really depends. So like in this case, we can say that our, no, that's really, yeah, that's it. And then our ds, same sort of idea. ds is actually the same as before. So here, right, our ds is still the square root of 1 plus 2x quantity squared. We're not going to be able to finish this one, by the way. I just want to point out that like it's something totally different. So if we do this, we get the integral from x equals 0 to x equals 2 of 2 pi times our radius, which is x squared, times again the square root of 1 plus 4x squared dx. And this one we would require trig substitution for. There is no other way to attack this one. So this one definitely need trig substitution. It's probably even still pretty gross after that, but yeah. Now I want to mention here, because I can, we could have set this one up differently if we decided to. We could have instead said, how much time have I got? Okay, I got time. We could have said, well, I know that y equals x squared. I could solve for x in terms of y and write y equal to x equal to plus or minus the square root of y. That would have been totally valid. Specifically, this top part is x equal to the positive root of y. This bottom part is x equal to the negative root of y. Am I saying that right? I feel like I'm not saying that right. Does that seem right to you? It doesn't seem right to me. No, it's not. This bottom part's not. I'm being dumb. the left part over here would be x equal to negative root of y. Right, right, not the bottom part down there. Fine, it's okay, we don't need that. So then what we could have said instead is, okay, our surface area of our band is 2 pi times the radius times the ds. But here, if we're doing things in terms of y, our radius is just y. And our ds is the square root of 1 plus, well, now since we're writing x as a function of y, it's dx dy squared. So when we did it in terms of x around the x-axis, the radius was whatever the function was, y equal to f of x. But when we go in terms of y, the radius is just y. So in both instances, you're using the same thing for the radius. It's just that in one of them, you have to use the variable y, and the other one, you have to use what y is equal to as a function of x. But you have the option kind of doing either one whenever you want. It just depends on what makes the most sense. And then here are dx dy. Well, if x is equal to y to the 1/2, your dx dy would be 1/2 y to the negative 1/2, or 1 over 2 root y. So then, if we do this, our surface area of our band is going to be 2 pi times y times the square root of 1 plus 1 over 2 root y squared. And so if we were going to find the surface area in general, it'd be the integral from y equals 0 to y equals 4. Right? If x is going from 0 to 2, y is going from 0 squared to 2 squared. And then we're going to get 2 pi times y times the square root of 1 plus 1 over 4y. It's kind of neat. But still isn't better. So the funny thing about these kind of problems that I've seen over the years is basically if doing it one way is kind of impossible, doing it the other way is also usually pretty impossible. Whereas if it's doable, either way, it's usually doable. Maybe sometimes one way seems easier than the other, but they're kind of either impossible or not. And switching which variable you're using doesn't really make it more or less possible than it was before. Okay, well, let's look at an example we can actually do. Ooh, yeah, that's a fun one. Okay, so let's say we want to find the surface area of y equal to the square root of 2x minus x squared. Again, x going from 0 to 2. X should definitely be limited to be in the domain of whatever function you have, right? We don't want weird values that aren't in, and here we have that. This function kind of looks like, I don't want to say it does. It kind of looks like the top half of the circle, but it's not really. But it definitely does. If x is 0, you get 0. And if x is 2, you also get 0. So it kind of looks like this. We're revolving around. Here, solving for x as a function of y, although we maybe could, is not really a good option, right? I don't want to do more work than I really have to. So if it seems like y is pretty stuck as a function of x, we should definitely carry on like that's the truth. So we're going around the x-axis. I know that my surface area of my band, as it is every time, is 2 pi times the radius times ds. Okay, I want you to get this stuck in your head. If we're going around the x-axis, what's the radius? Is it x or y? Y. Always y. It's just that sometimes we then replace y with what it's equal to as a function of x. So when I'm thinking for this around the x-axis, I'm like, okay, that's 2 pi times y. And then my ds, well, since I have y as a function of x, I should write it as the square root of 1 plus dy dx squared. Dx. But that dx is telling me, I am stuck with things being functions of x. I need my variables to be in terms of x. So this y has to get replaced with the function of x that it's actually equal to. Right? We're really just asking how far away is this little piece from the x-axis? Oh, it's y away, and y happens to equal this function of x. So if x were 1, for example, our radius would also be 1, because 2 minus 1 is 1, and the square root of 1 is 1. So here we end up getting 2 pi times the square root of 2x minus x squared times the square root of 1 plus, the derivative of that? Ugh. Let's find that real quick. dy dx is 1/2 my stuff to the negative 1/2 times the derivative of my stuff is 2 minus 2x. That's looking really gnarly. Fine. I would definitely choose to do a couple things here. Simplifying becomes important in this process. Simplifying your stuff actually does really matter. So if I factor out a 2 here, I can see that this is really equal to 2 times 1 minus x over 2 times the square root of 2x minus x squared. The 2's cancel. And then if I square this, because I am going to have to square it, dy dx quantity squared is 1 minus x squared over 2x minus x squared. And that's what I'm going to plop in there. Now, when you've got square roots times square roots, it's usually a good idea in this process to combine them into one square root of the stuff times the other stuff. Also, I am noticing that this 2x minus x squared here is the same as the denominator over here. So if I multiply this 2x minus x squared through this other stuff, I'm going to end up getting rid of the denominator, which is great. So I'm going to get, and let's write out the whole integral for the surface area. The surface area in total is going to be the integral from x equals 2 to, from x equals 0 to 2. I'm going to get 2 pi times the square root of 2x minus x squared times all that. 1 plus 1 minus x squared over 2x minus x squared. You're welcome. I will point out as you leave, this kind of thing happens a lot as well, where stuff ends up canceling nicely if you bring it all together in one square root. So then if we distribute this, we end up getting the integral, let's bring the 2 pi out in front. 2 pi times the integral from 0 to 2 of the square root of 2x minus x squared times 1 is just 2x minus x squared. And then 2x minus x squared times this fraction, the denominators are going to cancel. And we're going to get that 1 minus x quantity squared. And then the hope here is that things are going to simplify. I know so I will say these surface area problems get messy. There's kind of no way around it. So if we do this, we get 2 pi times the integral from 0 to 2 of the square root of 2x minus x squared. And 1 minus x quantity squared is 1 minus 2x plus x squared. Here's where it seems extra dumb. Look at what cancels. I'm left with the integral of 1. So I get 2 pi times the integral from 0 to 2 of the square root of 1 is 1. Fun fact, when you're integrating a constant, you just get that constant times the length of your interval. So we could do the work and say it's going to be 2 pi times x from 0 to 2, and then plug in the 2 and the 0. But really, we should know at this point that when you integrate a constant, you just get that constant times the length of the interval, which in this case is 2. And then our 2 times 1 times 2 pi gives us 4 pi. Cool. Kind of weird. I can keep my papers in order here. Okay. Yeah, I don't want to do that problem. Oh, that problem is cool though. Okay, let's do one more. Let's go back to the usual. So here's, let's say now I wanted to take my, what example do I want? Yeah, let me grab my, I took pictures from the book. So I was like, let me grab one. let's say we wanted to find the surface area of, let me think for a second about how I want to do this. One moment. Yeah, let's do x that. Yes, okay. Let's say we've got x equal to y cubed over 6 plus 1 over 2y from y between 2 and 3. Surface area of that revolved around the y-axis.
Just because we know this type of thing, you just know the answer is gonna be a negative, right?
Well, but the thing is, there's more to it this time. You're not, well, actually, yeah. So the thing is, for surface area, we don't just get to flip the sign of this. Part of the pattern still works the way we think it's going to work, but let me just point out what's going to happen. So we're going to find our surface area of our band. As usual, is going to be 2 pi times your radius times your ds. Okay, first things first. Well, actually, let me say, we can see that x is written as a function of y, and we're kind of stuck with that, right? There's not a good way to solve for y here. It's probably impossible. So we know that we need to be doing things in terms of y. So we know it's going to be 2 pi times whatever the radius is times the square root of 1 plus dx dy squared. Right, we're differentiating this x as a function of y with respect to y. Okay. If we're going around the y-axis, you don't have to draw a picture to know that the radius is which variable. Right, it's x. So the radius is x. But as you can see, that presents a problem. Right? I've got an x when I want a y. Right? Maybe my curve looks like, I don't know, maybe it looks. Right, exactly. So maybe my curve looks like this. I'm taking, this little bit here, and here's my radius, which is how far we are away from the y-axis, which is the x value. So my radius is x, but then we're going to replace x with what we know it's equal to. Cool. So now the thing that happens in the square root from before still happens again. I know that when we take the derivative and square it and then add 1 and then square root it, we're going to get back essentially the same derivative, but with the opposite sign. Let's do it. Yeah, we got time. Let's do it real quick here. So I definitely do recommend writing this in a way where it's easier to differentiate. So dx dy, I didn't do the thing I said. X is equal to 1/6 y cubed plus 1/2 y to the negative first. So then the derivative of that is going to be 3/6, so 1/2 y squared minus 1/2 y to the negative 2. And look, we see the same sort of pattern arising here, where the powers of my variable are opposite signs of each other. So I know when I square this thing and multiply it by itself, you're going to get things in the middle canceling out. So dx dy squared is going to be first term squared. What should my middle term be? If I want it to work out the way it's always worked out. Say it one more time, sorry. Yeah, that's it. It should turn out to be negative 1/2. Let's double check. If I multiply 1/2 y squared times negative 1/2 y squared, I get negative 1/4 y to the 0th, but I get 2 of those. So I get a negative 1/4 plus another negative 1/4, which is negative 2/4, which is negative 1/2. The middle term has to come out to be negative 1/2, so that when you add 1 to it, it just changes signs to positive 1/2. Right, but only negative 1/2, right? Negative 1/2 is the only negative number that you can add 1 to and have it become its positive self. Right? There isn't any number that does that, any other number that does that. So then we add 1, and 1 plus dx dy squared is going to be exactly the same thing, except 1/4 y to the 4th plus 1/2 plus 1/4 y to the negative 4th, which we know has to factor like this, except with a plus sign in the middle. So it's going to be 1/2 y squared plus 1/2 y to the negative second quantity squared. Okay, so then we can say that our actual surface area is going to be the integral. Let's put the 2 pi out in front from y equals 2 to y equals 3 of our x, which is really, we should be replacing with the function of y. That's going to be y cubed over 6 plus 1 over 2y. That's my radius. And then times this whole ds mess, which is going to be the square root of this thing here. 1/2 y squared plus 1/2 y to the negative second quantity squared. It feels a little silly to write that stuff. I probably could have just gone to the next part, but it's good to see that, oh yeah, that is my ds, which is equal to the square root of 1 plus dx dy squared. I should mention at this moment, just because it's worth mentioning, that if instead we were going around the x-axis, the formula would be exactly the same, except instead of having this here as our radius, well, this is still in terms of y, but it would, instead of being x, it would be y, just straight up y, nothing super complicated. It would literally be the integral of y times all this, which would probably be easier to do, but okay. So then we simplify, we get 2 pi integral from 2 to 3 of y cubed over 6 minus 1 over 2y times, I'm going to write this as 1/2 y squared plus 1 over 2y squared. And then it's just multiplying stuff out and then doing the integral. It's not pretty, but it's also not that terrible, right? It's just powers of y. So y cubed over 6 times 1 over 2y squared is 1/12 y to the 5th. And y cubed over 6 times 1 over 2y squared is going to be 1/12 y. And then negative 1 over 2y times 1 over 2 times y squared is going to be negative 1/4 y. And then finally, 1 over 2y times 1 over 2y squared, or negative 1 over 2y, 1 over 2y squared is going to be 1 over 4y cubed. And I would probably simplify a tiny bit, since I do have these two things with the same power of y. I would say that's, I've got 1/12 y minus 3/12 y. So that's going to be negative 2/12 y, which is negative 1/6 y. So I'd rewrite this as 2 pi integral of 1/12 y to the 5th minus 1/6 y minus 1/4 y to the negative 3rd. From 2 to 3. And I would stop there since it's 2 o'clock. Saved by the bell. This one, so I should say, this is not too terrible to integrate. It's not nice, but it's just a mess of, right? You're going to get 1/12 y to the 6th over 6 minus 1/6 y squared over 2 minus 1/4 y to the negative 2 over negative 2. And you're going to plug in 2 and 3. And then it's just, it's a mess, but it's not like the worst thing you've ever seen in calculus. So you get 12 times 6 is 72. All right, I mean, it's done, right? 3 to the 6th over 72 minus 9 over 12 minus 3 to the negative second over negative 8. And then you plug in 2 and you do the same thing, right? 1/12 or 1 over 72 times 2 to the 6th minus 1/6. 2 squared over 2 is 2 minus 1/4. 2 to the negative second over negative 2. Right? It's not nice, but it's totally fine. So, surface area. Not too bad. I'll leave you with arc length is the integral of ds. And surface area is the integral of 2 pi r times ds. And then I should just add on, if you're going around the y-axis, then your radius is x, which could be the function of y. And if you're going around the x-axis, your radius is y, which could be a function of x, depending on which variables you want to use. All right, I should stop talking. 202. You're welcome. Oh, sorry, you can't see that part there. Sorry about that. Anytime.